Let's see a few animations first, and then we get into the lecture.
Welcome to the world of physics. Today, we will explore work done by force. We'll look at constant and variable forces. See how pushing this box creates work.
When a force acts on an object, causing a displacement, we calculate the work done using this formula as the work. Force applied. D is the magnitude of the displacement.
Class 11 Physics, Chapter Work, Energy, and Power. In this video, we'll cover everything from work done by forces to kinetic energy, potential energy, power, and collisions. Let's begin our journey into one of the most fundamental topics in physics. First up, work done by a constant force. Work is defined as force multiplied by displacement in the direction of the force. The formula is W equals F dot D, which is FD cosine theta. Here, theta is the angle between the force and displacement vectors. If the force helps the motion, work is positive. If it opposes motion, work is negative. And if force is perpendicular to displacement, no work is done. For example, carrying a bag while walking, your upward force does zero work because displacement is horizontal. Now, what if the force changes as it moves? That's a variable force. You can't just multiply. You need to integrate. Work equals the integral of f of x dx, which is the area under the force displacement graph. Think of stretching a rubber band. At first, it's easy, but the more you pull, the harder it gets. The total work you do is every little bit of stretching added together. Kinetic energy is the energy an object has because it's moving. The formula is K equals half mv squared. Notice the velocity is squared. That means if you double your speed, your kinetic energy quadruples. That's why high-speed crashes are so devastating. A heavy truck moving slowly has lots of kinetic energy. A bicycle moving fast has less because it's much lighter. The work-energy theorem is a beautiful connection. It says the net work done on an object equals its change in kinetic energy. W net equals delta K, which is half mvf squared minus half mvi squared. If net work is positive, the object speeds up. If negative, it slows down. This bridges force-based analysis and energy-based analysis. Think of kicking a football. The work your foot does equals the kinetic energy the ball gains. Power is the rate at which work is done. Average power is work divided by time, measured in watts. 1 watt equals 1 joule per second. Instantaneous power is force times velocity. Two people climbing the same stairs do the same work against gravity, but the one who runs up in 5 seconds has 4 times more power than the one who walks up in 20 seconds. Power is about how quickly you can get the job done. Potential energy is stored energy due to position. Gravitational potential energy is given by mgh, mass times gravity times height. A book on a high shelf has more potential energy than one on a low shelf. You did work to lift it there, and that energy is stored. If it falls, that stored energy becomes kinetic energy. Only the change in potential energy is physically meaningful, so choose a reference point and measure from there. Now, a spring stores elastic potential energy. Hooke's law says the restoring force is F equals minus kx, where k is the spring constant and x is the displacement. The negative sign means the spring always pulls back opposite to how you stretch it. The energy stored is half kx squared. Notice the square. Pull twice as far and you store 4 times the energy. A slingshot works exactly like this. Let's talk about conservative versus non-conservative forces. A conservative force, like gravity, does work that depends only on your starting and ending points, not the path you take. Take any closed loop and the net work is 0. Energy is stored and can be fully recovered. But non-conservative forces, like friction, depend on the path. Slide a box across the floor and back to where you started. You did work, but the box is back where it began. That work turned into heat, which Motion in a vertical circle, like a roller coaster loop. As the object moves up, kinetic energy converts to potential energy. At the top, potential energy is maximum and kinetic energy is minimum. At the bottom, it's the reverse. To complete the loop without falling off, the minimum speed at the top must be the square root of g times r. This is where centripetal force equals the weight. The total mechanical energy stays constant throughout. Finally, collisions. In an elastic collision, both momentum and kinetic energy are conserved. Objects bounce off each other like billiard balls. In an inelastic collision, only momentum is conserved. Kinetic energy is lost to heat, sound, and deformation. In a perfectly inelastic collision, the objects stick together like two lumps of clay. For two-dimensional collisions, you apply momentum conservation separately in the x and y directions. Let's recap the key takeaways. Work requires both force and displacement. Kinetic energy scales with the square of velocity. The work-energy theorem connects force and motion. Power measures how fast work is done. Conservative forces like gravity store and recover energy, while non-conservative forces like friction dissipate it. In elastic collisions, objects bounce. In inelastic ones, they stick or deform. And remember, energy is never created or destroyed. It only transforms from one form to another. Thanks for watching.
Video by Anand Mohandas.